In this lesson, we will review basic properties of logarithms, mainly logarithms to the base 10. And we will also answer the question, what are logs good for? I know this is a topic that baffles a lot of algebra students, and I hope that this presentation will bring some clarification to this subject. For the purposes of this lesson, we will assume that logarithm represents, so if we write log of x, let's assume that that means logarithm base 10 of x. And we're only going to emphasize base 10, and if you can grasp base 10 really well, I really believe that you'll be able to transfer this knowledge to other bases, whether it's base 2 or base e or any other bases. So, but for this lesson, remember, log means log base 10. So if we're trying to find log of 10 to the 5, the answer is simply 5. And just to remember why that is, basically, a logarithm of 10 to the 5 simply returns the power 5. So when you take the log of any number, the answer you get represents a power, and that power is the power you raise 10 to get the value. Let's do a few more examples. Say log of 10 to the 7. It simply returns the power, which is 7. So you can think of this as a way to simplify numbers. When you're dealing with a really large number, you take the log of that and returns a very small number, such as 7. Imagine working with 10 to the 7 versus 7. 7 is so much easier. So logarithms, in a way, by just working with the exponent, they reduce the problem to some simpler values, and they make it easier to work with in certain circumstances. A few more examples. Log of 10 to the negative 7. By the same idea, it's just going to be negative 7. Log of 10 squared, same idea. And what if you just have log of 10? Well, there the hidden power is 1, right? So the answer will be log of 10 to the first power, or log of 10 simply is going to be equal to 1. Okay, now let's ask the question, log of 25. If we could just write 25 as 10 to a power, the answer would be whatever that power is, right? Now, at the moment, let's try to do this by trial and error. Well, 10 to the first is 10, 10 to the second is 100. So somewhere between 1 and 2 lies our answer. And if we check, so I'm going to try 1.5. So what is 10 to the power of 1.5? Okay, that's too much. We're trying to get to 25, right? So let me try 10 to the power of 1.4. And there the answer is very close to 25. So we estimate the answer is something to be very close to 1.4. So we can say 25 is, roughly speaking, 10 to the 1.4. And therefore the answer to this question is going to be 1.4. Now, luckily, you don't have to do this trial and error every time. There is actually a specific logarithm key in your calculators. You can simply enter log of 25 and it will return the correct answer. And we expect to get something very close to 1.4. Let's see. So simply enter log, comes with a parentheses, just enter 1. We want log of 25. And the answer, just like we expected, something very close to 1.4. Specifically 1.3979 and so forth. So the nearest tens, again, you would run that as 1.4. Now let's ask the reverse question. Log of something is equal to 5. Can you guess what that something is? The answer is, of course, going to be 10 to a power, and it's going to be 10 to the 5. Similarly, if log of x is equal to 3, can you guess what x is? x should be 10 to a power, in this case 10 to the third, right? Think backwards. Log of 10 to the third would be equal to 3, right? And one last, what about if log of y is equal to -1, what is y? Similarly, just like the last example, you would say y is equal to 10 to the -1. So logarithm of a quantity returns the power of 10. So if logarithm of a quantity is -1, that quantity had to be 10 to the power of -1. So based on what we've done so far, we have the main definition of logarithms, and it tells you how to go back and forth from logarithmic form to exponential form. And here it's stated as base 10. So if log of x is equal to a power, then x must be 10 to that power. Or vice versa, if x equals 10 to a power, then log of x must be equal to that power. So this is the most important rule, basically used as a definition of logarithms. And you learned also two more important rules in algebra about logs. Let's also briefly review those, and then we'll take a look at some important applications of logarithms. This one pertains to log of a product. For example, log of 10 squared times 10 to the third. If you simplify this product, you would have to add the exponents is log of 10 to the 5. And based on everything we've learned so far, log of 10 to the 5 is 5. Notice that 5 is the same as the sum of 2 and 3. Another example, log of 10 to the third times 10 to the fourth. Same idea, add the exponents, you get log of 10 to the 7. And from based on what we got over here, log of 10 to the 7 is 7. We can generalize this. In general, log of x times y, in this case that is our x, and the other quantity is our y. So if this is your x, then this is your y. Then you can write it as a sum. It's the sum of the powers, and the powers are basically log of x and log of y. So log of the product x times y equals log of x plus log of y. This is another very important rule, converting products into sums under logarithms. And the last special rule that we're going to review is the following. Basically, if you have log of 10 to the r, of course the answer is r based on everything we've seen so far. But you can also write that as r times log of 10 because log of 10 is 1. But more generally, if you have log of x to the r, you can write it as r times log of x. So here, in the above example, it was log of 10 to the r is r times log of 10, but more generally, log of x to the r equals r times log of x. So these three rules really make up, I would say, the most important rules about logs. This one being your rule number 1, this one being your rule number 2, and this one being your rule number 3. Okay, now some applications. So the first important application of logs is that it makes it, when you take the log of a number, it makes it easier to deal with especially large or small numbers. So log of a million, again a million or 1,250,000, whatever it may be, a large number, if you're going to multiply those together with other large numbers, it's tedious. But if you take the log of that number first, you get a small number, such as in this case a 6, which is much easier to deal with. So logarithms make it easier to deal with large or small numbers. Same thing like log of 50 million is just 7.7. Log of this very small number is -8. Again, a whole number. Usually those are much easier to deal with than extremely small or extremely large numbers. example of this is from chemistry, the pH scale. pH is defined as negative log of the hydrogen ion concentration. For example, if the hydrogen ion concentration is 10 to the negative 5 moles per liter, then what is the pH? Let's plug 10 to the negative 5 into this formula. And notice 10 to the negative 5, is a number perhaps not so user-friendly, but look at the output. When you plug that into the pH formula, you have negative log of 10 to the negative 5, and log of 10 to the negative 5 is, based on the examples we've done, simply negative 5, right? But then there's another negative in front in this formula, so you'll have negative of negative 5. The answer is 5. So instead of dealing with something that doesn't look so friendly, like 10 to the negative 5, instead they have converted this to this number, which is much easier to work with, simply 5. So pH is basically converts the concentration of hydrogen ions into a much more easier to work with format. And here's a nice picture that I got from epa.gov. And it shows us that a pH can be anywhere from 0 through 14. When it's 7, it means neutral. Anything less than 7 and further closer to 0, it becomes more and more acidic. And if you have a solution with a pH that is higher than 7, that is and closer to 14, it becomes more and more basic. And it gives you some examples of solutions that are basic, example of things that are more acidic. But the idea is pH can be a number between 0 through 14. That's because the formula has a log and it has converted these unfriendly numbers into nice and easy to interpret values. So typically, if you were not using logarithms, you would have to deal with 10 to the negative 0 through 10 to the negative 14. Not so nice and not so easy to work with, perhaps. So by taking the log of this, you would have negative 14. And then by multiplying that by negative 1, you would have 14. So each of these numbers have been converted to a nice whole number, a positive number as well, or 0 on that pH scale. Another example of logarithms is that they help us solve exponential equations. And exponential equations are equations of the form where the unknown appears in the exponent. Say you want to solve for time, and I'm assuming that most of you are familiar with this equation, A equals PERT. You might have seen this in your algebra classes about finding the accumulated value of money, P dollars invested at R% interest, R being in decimal form, for T years. And so suppose you know that you want to end up with $10,000 and you're investing $3,000. Your interest rate is 7%. But the question is, how many years should we invest this money for? The unknown is in the exponent. Now, if you happen to have a situation such as t to the third power equals to a value, how would you solve for t? You would take the cube root of 100. If you had t plus 3 equals to a number, how would you solve for t? You would subtract 3 from both sides, right? But how do you solve an equation where the unknown is the power? You cannot take the cube root, you cannot take the 7th root or even the tth root. What you have to do in that situation is apply the inverse function. And that is the logarithmic function. So this is a very important application of logs, that they help us solve equations where the unknown appears in the exponent. To solve this equation, we would normally begin by dividing both sides by 3,000. So 10,000 over 3,000 is the value that we got there. And then you would apply log to both sides. Ordinarily, you would apply natural log, which is base c, but for the purpose of this lesson, we're only dealing with base 10, so I don't want to complicate matters. I'm using base 10. So here we have log of 3.33 equals log of the right-hand side. And log of 3.33 is a number you can obtain from the calculator. This side you can simplify based on the third property. This power can come to the front as 0.07t. And log of e is something you can calculate on the calculator as well. Now it's a matter of dividing both sides by 0.07 times log e, because that way you're going to isolate t all by itself. And if you do all of that and evaluate that on the calculator, you will get t equals about 17 years. So if you invest $3,000 at 7% for 17 years, you'll end up with $10,000. And here we assume that interest is compounded continuously. And here is one of my favorite applications of logs, that logarithms transform some graphs into a clear and easy to interpret form. And I have one of my favorite graphs I'm going to show you guys from www.gapminder.org. So let's go over there and take a look. Okay, so let me begin by showing you the original graph. This is the original graph. You have income per person in different countries, and on the y-axis you have life expectancy of the residents of those countries. But you see what's happening is some countries, there's a lot of countries that where the income per person is very low, which is much less than 20,000. But then there are some countries way out here near 100,000 and near 80,000. There's some dots, as you can see there. So it's hard to do justice to this graph when so many points are scattered, and it's not easy to see what's happening on the left-hand side over there. So the solution is to take the log of the incomes. So right now, we're trying to put so many numbers. There's so many small numbers over here, perhaps less than 1,000, less than 5,000, but yet we're also trying to squeeze in numbers like 100,000 on the same graph. So when that is the situation, you have some very, very small ones and some very large ones, and you're trying to see a better scattering of those values, what you do is you take the logarithm of the value. So let's do that. So I'm going to take the logarithm of all the income values. And now look at what happens. The graph, the points got scattered much better, and you're able to see the situation a lot better, and the graph is much more easily interpretable, and overall it's just a much better graph in my opinion. And that's why they're giving you the option to convert into logs and to look at the situation like that. Now let's see what happened here. So it's putting basically values from 400 all the way to 100,000. But technically, it's not really plotting the 400 because we selected the log option. Technically, it's graphing the log of 400 all the way to log of 100,000. Let me go back to my notebook to show you something here. Let me unveil my graph here. I want to show you because here's what I did with the scale. At the bottom, I found what is log of 400. The answer is 2.6. I found log of 1,000. Of course, we all know that right now. Log of 1,000 is 3, right? Then log of 10,000, again, because that's 10 to the 4, that's 4. Log of 100,000 is 5. You see, like from 3 to 4, this is like considered to be 1 unit on this graph, from 4 to 5. You see the difference between 400 and 100,000 when converted into logs is not that much. It's only from going from 2.6 to 5. And you can easily fit all those values nicely into this graph. And then you can see what's happening to the data in the logarithmic scale. So that's another good application of logs. And there are many other ones, but for the brevity and for this lesson, we've only highlighted 3 of those. And as you can see, logarithms are really not that bad. They have a bad reputation, but they are actually quite useful for the sciences. So I hope you'll get lots of practice, get comfortable, and keep using logs.